Okay. Should we start?
Yes, please.
Okay, wonderful.
Yeah.
Hi, everyone. Good morning. My name is Abdullah. And here's my friend Chris. And today we're going to talk about our project and focus on feedstock production for forestry seed reconstruction. So the project goal.
Hang on, Abdullah. Are you guys getting sound online?
You want me to unmute myself?
Okay, we're good for sound. Okay, well, that's fine.
We're
You
good.
guys can hear in the back. Great. Okay, great.
Should I continue?
Yes,
Okay,
please,
perfect. So the project goal is to replicate the work of Don Heath in the reconstructing CD scan from a limited number of projections, allowing for reduced ionization exposure. Also to analyze the robustness and generalizability of using deep learning approaches to reconstruct CD scans by analyzing performance with noise and unseen bodies and scans. This was contingent on time if we were able to finish it, and probably we were able to finish it. So it's basically to see if we can break the model. The outline of the presentation is to talk a little bit about CT and exposure to radiation, acquisition, projection sampling, and having enough data, deep learning in general, to have a brief intro for those who are not familiar, reconstructing CT scan from limited projection by deep learning, analyzing the results and comparing it with filtered back projection, and finally seeing if we can break it and how it would break.
Okay, just a quick recap. This is a CT scanner on the left. There's no denying how useful they are. In the US alone, 70 million CT scans are taken annually. While these are really good medical diagnostic tools, the one caveat is the harmful ionizing X-ray and radiation. And particularly what's of interest is the carcinogenic properties of it. And just to summarize what you're seeing here, a typical CT scan for abdominal and pelvis CT can give you 8 to 14 millisieverts of radiation. And putting that in perspective, just being outside for a year, you gather 3.11 millisieverts. So roughly 4 times the amount in one dosage. And the Committee for Biological Effects of Ionizing Radiation, they say there's no threshold to this. It follows a linear fashion, and for 100,000 cases, you'll get roughly this many cases of cancer leukemia per 100 millisieverts of exposure. As they said, it follows a linear threshold and no threshold, and there's the need to expose our patients to this radiation, and for modern CT scans, they follow principles that are guided by the NICO theorem. And on the left, you'll see a case of undersampling. And for what was in demonstrating class is a generalization or approximation when we said delta theta equal to delta R. And so kind of applying this to our 64 by 64 images, the required number of angles is roughly 57. And what we'll see in our project is that we can actually go below that number and still get subjectively good images.
So we're going to talk a little bit about deep learning, because it's basically the basis for our project. Deep learning is a subfield of artificial intelligence. It's used in neural networks with many layers as the main intelligence learning unit. It's a subfield of artificial intelligence and machine learning. The neural networks are formed of layers, as just mentioned, where the output of each layer is fed into as the input of the following layer. This is like the simplest form. There are more complex forms of that. So if we look at an example, they've been really good at extracting features and analyzing semantics in images, reconstruction, classification, and object detection. Here we can see that the output pixels of the image are fed to the layers of the network, which are 4 layers. And then at the end, we can predict what number is in that image. We have an input layer, 2 hidden layers, which are the layers in between, and then an output layer. Now, the basic building block of this is what we call a neuron. Neuron basically, in the simplest form, have weights and biases. These weights and biases are combined in a linear fashion with the inputs. And then there is a nonlinearity of the output that generates the output. This nonlinearity is basically what generates the power of neural networks, its ability to predict really complex functions. So this weight could be any linear, not any, but mostly any linear operation, such as wave multiplication in the fully connected layer, or convolutional operation, which is basically a linear operation. In our work, we're working with convolutional neural, which are really good at extracting semantics from images and other presentation. So CT reconstruction using deep learning, there are two approaches. The image space approach, which is basically a neural network is trained to match an image after it's been reconstructed to an image with no noises and artifacts. So its goal is basically to reduce the noise and artifacts in the image. If we can see here a simple procedure, how it works, you get the cenogram or the projection, and then you do the reconstruction using, like, for example, filter back projection. Then you use a deep learning model to basically remove these artifacts. So in a sense, they're not actually reconstruction, more of a denoising, artifacts removing. The other approach is the projection space approach, where a neural network is trained on the projection to match them to the actual scan. That means it's learning an enhanced form of the inverse radial transform. A series of convolutional neural layers are trained to understand and know that mapping and to perform. It can be used to reconstruct from a limited number of projection. It's what we did in our project, in the goal of either and reducing ionization and improving the construction quality. So if you look here, a general structure of the network that we're using, I'm going to go into a little bit of detail about it. But in a sense, this approach can be considered as true reconstruction. The model is still enhanced inverse radial transform in the sense that it does not only do the inverse radial transform, it does remove the artifacts. It produces improved, as we can see, reconstructions versus the filtered back projection. And the paper only 16 angle views, so 16 theta, 16 values. Only we explored the possibility of 4, 8, 16, 32, and 64. So what we do here is basically we took the cenogram, we take each projection and then stretch it with corresponding to the angle that it was applied at. So we're not doing any basically that projection. And then we're feeding that into the convolutional neural network with different 15 layers, mapping these projections into the reconstructed scan. This is as simple as it gets. If you want more details, we can do that. So to do this, we created the data for the training ourselves. We created object with different random intensity. As you can see here, they're overlaid without overlapping, generating random number, not random shape, random size all over the image space. Then what we did is we bounded them with an ellipse representing some kind of a body shape. Also, the ellipse size, orientation, and location is random. After bounding, it looks something like this. So it's bounded by that ellipse. We also created another data set where we overlaid ellipses that are of increased intensity. We added the intensity over and over again. We trained the network. Every iteration, we generate a new data set. So over all the epochs, we basically trained the network on 320,000 images of these so that we can create proper coverage of the image space to do robust reconstruction.
Now for the fun part, we show our results. Like we said, we neurotically kind of followed powers of 2. So we went 4, 8, 16, 32, 64. And of course, on the low end, we're kind of breaking it here. It's very blurry, the neural network's reconstruction. And of course, when we increase the number of angles, we see maybe at 16, it's like subjectively pretty good. And beyond that, of course, it's roughly exactly the same. And then we went and compared that to filtered back projection. So we have side by side, left is the original neural network output, middle, and right is filtered back projection. You'll notice on filtered back projection, there's a lot of smearing. As we're well below what's required to reconstruct this image, but we don't have that issue of the smearing with our network. It's just the blurriness. And as we continue, it gets better. And say when we get to 16, it looks subjectively good. And we still see the smearing with the filtered back projection at 16 and even 32. It's kind of faint, but it's still there. And like I said, somewhere around 57 is the number of angles that's required. So once we get to 64, it looks pretty clean. Anyway.
So in addition to that, we also tried to break the network and see if it breaks worse than filtered back projection. This is something we discussed with Professor earlier. It was a fun part of the project, so we added different level of noise, and we wanted to see if the model is going to break first or filtered back projection. Now, with all the views, you can see here the network, even though with high noise level, it failed. It still outperformed filtered back projection, which was very interesting. Something that not quite especially at higher views. The same thing with bodies that it hasn't seen before. It still outperformed the focal back projection. Body shapes, like it's like circles and rectangles, like that hasn't been trained on. So was able to reconstruct bodies. So, in conclusion, in this project, we were able to replicate the results of the paper proposed by Dong Yi, and I'm hoping I'm pronouncing that correctly, to reconstruct CD scans from undersample projections in terms of new angles using convolution neural networks. We expanded a little bit over the word, as I discussed earlier. The proposed model shows superior performance of tilted back projection reconstruction at a reasonable reconstruction time in the order of a few hundred milliseconds. The proposed reconstruction model showed a better performance when compared to a tilted back projection in reconstructing from noisy, as well as types of shapes of bodies that it did not see. However, this is an important thing. Neural networks and deep ones are really complex model. So for further investigation, it's really important for its robustness before it can be used for any clinical applications. And Professor Elliott has shown examples where sometimes these deep neural network reconstructions and it actually doesn't work or fails. And that's mainly due to the nonlinearity of the model. With that, I'll conclude and thank you very much. If you have any questions, please let me know.
Great. Well, congratulations. That's great. Get that thing working so well in such a short period of time. That's really tremendous. Question in the back.
Use the network to reconstruct. Like, have you tried to utilize the reconstruct
So what we're using is I can go back and show you. Yeah. What we're reconstructing too is the non-noisy one. So we're always trying to denoise. You mean, did we train the network on noisy images?
So
Did
train the network on my image and use the true label of the original one to try to like denoise the one image.
That's a great approach, and that's a great question. And that in the future, that should be definitely included in any deep learning. You should add the noise in training the network. We didn't want to do that because we had that analysis in mind at the end, and we wanted to add noise that wasn't there in the training and see how it's going to break into that. But it's definitely something you should do if you want to train this for any clinical.
Like, we have the math formula for reconstruction, and it's very easy for network to learn that math formula. But if you use that network to denoise,
Yes, if you have the complete number of projections, so if you go like to 180 and stuff, but the part of the project is actually to reconstruct from undersample. Like if you have 16 views, having the equation of the reconstruction doesn't matter because you're below the accuracy anyway. So you're not like, yeah, if maybe you have like 100, like what was the number, 60 to 70, like if you have a large number of angles, then definitely you can design a model to do other things than reconstructing from undersampled data. So definitely, yes, for sure.
Yeah, and I think it was pretty impressive how the artifacts just seemed to go away very quickly. Like it was 8 views or something like that, and then there didn't seem to be any streaking off the side. So yeah, another question.
If you compare the deep learning versus the back projection, did you compare any like parameters between the two, or did you like just visually compare them?
We did minimum square error analysis. We didn't include that. Like for the deep one, it was like very minimal, like 1 to the power minus 10 to the power minus like 3 and 4. And it wouldn't have like mean anything if we put like a table of 1 to the power minus 3 and then 1.4, 1.3. It's very low, so we wanted to show it visually. But yes, the mean square error is much less. But it's visibly like very powerful. But yes, if you compare the mean square error, which is, I'm going to be honest with you, the mean square error, if you train the network for a long time, you have to stop early. This is one of the techniques. I'm not sure if you're familiar with deep learning. You want to stop early a little bit because it could overfit after a certain amount of time.
Exactly.
Mean square error does after like, if you train it with, I think one of the networks we worked on, we trained for 1,000. Yeah, so Chris trained.
Well, that was with our prior data set. The new one that's training for 50.
50, okay. So like, yeah, I did one with like about 300, and it was at that higher number of inputs, so we started to overfit in the sense that mean square error, if you use it as metric, basically smoothes the image a little bit. I forgot the map, to be honest, which is embarrassing, but I remember this is a little bit smoothing system. I'll probably remove it again.
All right, great. That's terrific. We're gonna have to move on. I mean, one of the interesting things is your images, like when you look at an image like that and you say it was made in ellipses. So each ellipse has a, 4 parameters or something like that, and so basically that whole image can be captured in, 30 numbers or something like that, right? If you knew, oh, it's ellipses, so I'm gonna put an ellipse here, this angle, blah, 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 blah.
Yes.
And so the network can just learn how to put ellipses down, right? So but then it worked on squares, which is great.
No, because
Yeah.
it's not ellipses, because when you overlay them, if you look.
Oh, yeah, they get cut off.
Yeah,
That's
they
right,
get
that's
cut
right.
off.
Yeah, stand corrected.
For the,
Okay,
for the addition, that's
Yeah.
why we actually started with the.
that's right, that's right. We're gonna have to move on, but that's really good. Okay, next presentation. If you guys can stop sharing, we'll get sharing on the next one.
We use our microphone or we just.
You just go over there and use the mic on your computer, and that way people online can hear you, okay? Yep, fantastic. Okay, do a mic check maybe. On your computer basically, because we want to hear it through the computer. Just say something.
Okay.
Can you hear us?
Okay, good.
That's good. Should I mute it or no? Okay, okay, cool.
All right, so hello everyone. We are group number 8, and today we're gonna talk about filter effects on filter CT reconstruction, its application, and then filter design and optimization. All right, so first of all, let's go through a little bit of background. So what is CT? CT is computed tomography. So if you want to get a slice view of your body and view it top down, so the counterintuitive thing to do would be shining X-ray from head to toe, right? So we have to rotate the X-ray around our body, and we reconstruct an image from the 1D view that we get from the X-ray. And it works basically through the projection slice theorem, which says that a 1D view will give us a curve of intensities called GL theta. And then when you shine it through 360 degrees around your body, you get a bunch of GL thetas, and then it's basically a radon transform, which will give you a sinogram and from which you can reconstruct the image. So why do we need to use a filter? Because without a filter on F, image here, as you see, is going to be overexposed, and it is going to blur out all the little details that we want to see, like on the original image A. So filter back projection.
It's just not updating.
It just,
Slice.
it's not moving forward here. I mean,
Oh,
Okay, yeah.
oh, now.
All right, we're back.
All right, so the steps of filter back projection. First, we have a GL theta, and then we're gonna Fourier transform it. So the thing here is we're not gonna put a filter on the final image that we reconstructed. We're gonna apply it to the filter, the Fourier transform of the projection, and then we will inverse Fourier transform to get a filter back projection. So the filter here is what we're gonna play around with today to get different results. So the differences in filter, we have a RAM-like filter, which is you see have very sharp edges, so they weigh on high frequency. You have higher spatial resolution, but you have also more noise versus like the lowest one is the hand filter. You see we cut out all the high frequencies, so you blur out all the edges, the image will be more smooth, less noise, but then you lose resolution. The next thing we want to define first before we dive into that is sensitivity and specificity. So these are basically the parameters on how we define a good versus a bad CT scan. So sensitivity is the proportion of those who receive a positive result out of those who actually have the condition. And specificity is the opposite. It's the proportion of those who receive a negative result out of those who do not have the disease.
So for a second part, we did a simple analysis on some of those common filters mentioned, the ramp, Shep-Logan, cosine, Hamming, and Hahn filters, as shown. So to start, just give a brief background to our approach. We first created a 200 by 200 pixel modified Shep-Logan phantom, created a sinogram using the radon transform at 0.33 degree increments in that theta plane or theta direction. Added some noise, random noise, which was by default scaled to 1/10 the peak intensity of the original phantom, and added that to the sinogram to create a noisy signal. Then performed reconstruction using those 5 filters mentioned and the unfiltered situation. Here are the results shown. A couple things to note, and this will be a common theme throughout our presentation, are that in those earlier filters, the ramp and Shep-Logan, noise is obviously more present, more prominent than in like the Hamming and Hahn filters, which cut out those high frequencies more. But at the same time, in Hamming and Hahn, you get a little more edge blurring if you look closely at the edges of those different features as compared to those other filters such as ramp and Shep-Logan. So speaking more on the noise effects of those different filters, you can see there on the graph on the left that filters that weight high frequencies have more noise, as noise is an inherently high frequency type of feature. All the filters have some amount of high frequency weighting, so noise increases as compared to the unfiltered situation. And high noise can have a negative impact on specificity, as noise could potentially look like a disease state. As shown in the contrast to noise ratio graph in the bottom right, noise, when we were measuring a large feature, dominated the calculation of contrast to noise ratio, giving the Hahn and Hamming filters a better result CNR-wise. But if we take a look here at edge blurring, we take a look in the top graph at a large feature, just going over the edge of one, and 3 smaller features towards the bottom of the phantom crossing there. So we see something interesting here. First, obviously, with the original image in the top graph, you have that clear contrast between the feature and the background. It smooths out when you reconstruct without a filter. You see an interesting bump where the boundary is in each of the filtered situations, which makes sense. At the boundary, you have a high frequency component there. And so the filters are going to emphasize that some. But if we take a look at the lower graph, we see 3 features, 3 bumps in the original image. The ramp filter, you have clear contrast between them. Even if it's spiky at the top, you've got some clear bumps between each of the features. However, in the Hahn filter, that becomes smaller, showing that for small features, having that edge blurring can have a negative effect on sensitivity, as smaller features could potentially fade into the background, especially if there were more noise.
Okay, in part 3, let's take a look at the application of real-world cases. And we have a CT scan image, and there's a heart, and we are gonna focus on the dark area whose shape is like an inverted U. And when this happens, it means that the patient will have hypoperfusion in LAD perfusion bed, which could cause myocardial infarction. And so we done here is we add noise to this original image and use the different types of filters to see what happened. And the image with RAM and Shep-Logan filters, we still can see the dark area in the image, but it doesn't look clear. But when we look at the image with cosine, Hamming, and Hahn filters, the dark area are much more clear. So next we make the noise larger, and we can see the dark area in the RAM and Shep-Logan filters, but when we look at the cosine, Hamming, and Hahn filters image, we can still see the image right there. So in this situation, if the doctor get an image with the filters of RAM or Shep-Logan, he will tell his patient that his heart, he have no issues on his heart. But when he look the image with any other 3 filters, he will know that he's wrong. And that is what we call sensitivity. So here's another example. We have a CT lung scan image, and we'll focus on the ground glass opacities, which are caused by COVID. And we add noise on this image, and we still can see the outline of opacities in the image with RAM and Shep-Logan filters, but they are clear, obvious in the image with the other 3 filters. So with a larger noise. The ramp and Chef Logan filters didn't work, but they work with the image that with cosine Hamming and Ham filters. So there would be a chance that the doctor will make the incorrect diagnosis. So in summary, even though the edges are blurred more in the Ham and Hamming filters, the noise in Chef Logan and RAM filters makes CNR much worse, which will cause the incorrect diagnosis. So we find out that CNR is important for sensitivity. So we plot the 4 CNR figures, and based on these 4 figures, we got a ranking for sensitivity regarding the analysis and analyzed pathologies.
So for the last part of the project, utilizing the knowledge that we built in previous sections, we modified, created new filters, and combined other methods and considered real applications to just understand better the function and the characteristics of the filter and how they correlate. So firstly, we tried to tune a stock filter, an idea derived from PID filter tuning, to achieve like an optimized filter. So in our case, the parametric tuning is for the Hamming filter and it's presented by altering the coefficient A. We can see that for extreme values, the noise is aggregated, while for the 0.65 tuning, it's better, almost better than the stock one. And this can be seen from the CNR. So the same outcomes are drawn from the background noise and reconstructed images. And this makes 0.65 tuning a filter to be considered in later stages. So in the next part, we create new filters by stitching up, adding up, multiplying filters, or combining other techniques to create more targeted filters for our applications. So the final filters that will be considered is the winner filter, which is a signal to noise ratio optimization filter, our complex filter, which is a Hamming cosine hybrid, the tune filter that we saw before, and the hand filter, which is the best stock one. As we expected from the reconstructed images, our filter outperforms the other filters. Oh, sorry. Oh, I missed one. Sorry, I'm so sorry. So yeah. I'm sorry for that. So as we expected from the reconstructed images, our filter outperforms the other filters in both SNR and edge blurring and the background noise. An interesting point to make is that winner filter has a good SNR but high noise and an amplified signal, showing that SNR on its own is not a good parameter to consider for just the filter that we choose. Going back to our application, we can see again that our filter outperforms the tuned and the hand one and the other stock ones, with the others coming second, third. And thank you very much. Any questions? So
There we go.
sorry, what was your question? So it's this one and this one. So the whole thing we consider it being best because it has the best SNR ratio, it has the best blurring, and in our opinion, this is qualitatively again, we believe it makes the best image if you like make it like a bigger image. Yes, that's probably we tune it to this image. So for other images, of course, this limitation of the project, and as we mentioned before, we tune and we parameterize according to this one, and then we just applied it to another one just to check if this holds. Plus, this you could also see that this is like an image that has not a lot of high frequency, not a lot of density issues. Like if you try a more dense image, it will probably have worse effect on the quality.
The tuned Hamming.
Oh, probably.
Oh,
but,
yes, the complex filter as well. Yep.
yeah.
Yep.
Yeah.
I don't know.
It's probably a log scale. Yeah. Yeah, I'm sorry. Just like you. Like,
I didn't.
As opposed to a filter.
yeah. Yeah. That's it.
Yeah. So then inverting it, putting it back. Yeah. I know. Okay, great. Any other questions? Well, there you go. I mean, it's, in practically speaking, radiologists, when you give them images, they usually like highly filtered images. They like it smooth down, and probably for good reason, because you can see certain features like that in Park a lot better, right? Okay, great.
Thank you very much. Thank you.
Great. Can you guys hear me?
Yeah,
Yes, we can.
Awesome. Okay. Okay, we'll go ahead and get started then. I am Jonathan, and we have Jason, Javier, and Zaid in our group. And our project is the effect of varying CT's scan slice thicknesses. For a quick introduction, so calcium plaque is often detected using CT imaging. And this calcium detection is dependent on slice thickness, where slice thickness is the interval at which the image is taken. And this slice thickness is important because the kind of largeness of the slice thickness determines how much diagnostic value can be derived from the actual image that is taken. Additionally, slice thickness is correlated to the radiation exposure that is given to the patient overall. As the thinner the slice thickness, the larger the overall radiation exposure is. So there's this balance that has to be developed between the overall slice thickness and the image fidelity that is received, as well as the overall detection, as is evident by the picture on the right. So this project will examine the effect of modulating that slice thickness on overall calcium detection. And next, Jason will go ahead and introduce that.
So to go over the methods about what we did, we basically took original CT images that we consider our ground truth, and we added our own calcium to it. So then this will standardize things so that we take calcium through different slices, it might shift places. So we just standardize everything that creates an image is considered ground truth. Then we would take the radon transform of it using different projection numbers. So then since we can't really change the amount, the actual image that we get, because it's all standardized to a certain slice thickness. So then we had to basically do the radon transform, which will simulate taking different projections. So how that looks is basically you have this, the radon projection. So then over here, all these lines can be considered like one projection. So what we did was we modulated how many number of projections we have through this. So then what that looks like is how many detectors that would be the actual CT would take. So then this equation basically relates the slice thickness and the projection, where you have this root 2, 512. So then this basically normalizes it because the CT image is 512 by 512. So then if you take the projection along the longest diagonal, then that would be 1 projection per pixel. And with the pixel size of 0.7 millimeters per pixel, then our slice thickness would be 0.7 millimeters resolution size. So then we can divide this constant by our slice thickness. So that will give us the number of projections. So for example, if we want a slice thickness of 1.5 millimeters, then that would be 1 projection per every 2 pixels. And 2 pixel sizes is 1.5 millimeters. Roughly. And then this over here is basically you have this L. Changing that number of L is basically the resolution size. So to go over more of what we did, I'll hand it over to Saeed.
Awesome. So we applied these methods to a bunch of like open source CT scans we found of an 8-year-old patient who had pulmonary embolism. We did some multi image looking at the heart of the image more clear using like MATLAB, GIMP, and Fiji, where we inverted images colors. The heart is like more of like black rather than being white, because it was white initially. And then we also added our own like calcium, which was more as a Gaussian noise. Each added calcium had the diameter between 2 and 10 millimeters, going up in like steps of 2 millimeters. And then, so we had overall like 5 images with 5 different calciums. And then we simulated like 7 different slice thicknesses, shown here in the table for each like image we made. So we went from 0.7, because 0.7 millimeters is the size of 1 pixel, to up to 5. And then this 2.5 millimeter slice thickness is the industry standard. So this way we got to see like what would happen if we have a slice thickness below the industry standard, what would happen if we have a slice thickness above the industry standard. And so you can see as well, as Jason explained, the smaller your slice thickness, the higher your projections are going to be. And so just showing you like this was our ground truth. So these are 5 images we chose from a stack of like 189 images, because you can see like the hearts in the center of the image. We did an inversion, so we can make the heart like black, and so that our calcium be white, having more contrast. Each of the red arrows in the images point to where we added the calcium. On the left-hand side is where we have the smallest calcium of 2 millimeter diameter, and as we go towards the right, the calcium will increase by a diameter of 2 millimeters every single time, up to 10 millimeters. And throughout the rest of our slides, we will follow like this convention of having smallest calcium diameter on the left side and the highest on the right side. And these ground truth images will also be in every single slide after this one on the bottom, and on top will be our results. And Shabby here will take you through the first part of our results.
So basically, in the next few images, we're going to see how the calcium detection changes varying slice thickness. We're going to go from low slice thickness, lowest being 0.7 millimeters, to high slice thickness, highest being 5 millimeters. So as Say mentioned, the bottom 5 images here, they represent ground truth. The top images are the reconstruction images that we obtained. We're going to start with the 0.7 millimeters. As we can see here, we have the first is the 2 millimeter diameter, and we still get something here in the reconstruction. But let's focus our attention to the 10 millimeter, which we're going to see in every slide. The 10 millimeters for a 0.7 millimeter slice thickness, we're getting a good reconstruction. We're able to detect calcium really well. Let's go on to the next slide. So in the next slide, let's take our attention to the first image, the 2 millimeter one. As we can see, the calcium, you can barely see it. So eventually what we're gonna see is that the calcium is going to disappear. Meanwhile, in the 10 millimeter diameter image, we still get something, but not quite as good as the lowest slice thickness. Now going on to the 2.5 millimeter to the 2 millimeter, focus on the attention on the 10 millimeter diameter, it's getting a little bit more blurry. And as we go on to the 2.5 millimeter, you can see that we're still getting something, but it's not quite as good as the lowest slice thickness. And we're going to see what happens now as we go beyond the industry standard, and Jason's going to take over.
Thank you, Charlie. So now when you have the 3 millimeter slice thickness, I'm going to draw your attention to the middle slice. So this is the 6, it's probably pretty familiar, but this is a 6 millimeter slice calcium slice. So you can see that this is pretty faint now. It's starting to disappear, but then for the 8 and 10, you can still see some calcium is pretty obvious. So then we go to the 4.
the 4 millimeter slice. So the 6 millimeter calcium just completely disappeared, and then the same thing that's happening to the 8 millimeter now. It's becoming very, very blurry and almost like indistinguishable. But then the 10, you can still detect it. It's still there. I don't know how well you guys can see it in the back. But then for when you get to the 5 millimeter one, right, all up until 8 just all completely disappear, and then 10 starts getting more blurry, where you can't really see it. So then if you notice where all of these images started dropping off, it kind of shows the Nyquist spatial resolution of things. So at 3 millimeter slice thickness, we can still kind of barely detect the 6 millimeter calcium, 4 millimeter, the 8 millimeter calcium, and then now with the 5 millimeter slice thickness, you can barely detect the 10 millimeter slice thickness. And then so to talk about signal to noise a little bit, kind of looking at what's going on, we focus on the 6 millimeter calcium size because we found out that was a good balance between the ones that don't drop off too early, like the 2 millimeter one, and the 10 millimeter one, where it just is constant in every single test that we have. So then starting how this is organized is that the CT image on top is basically the inverse radon transform of our image, the reconstructed one with different size thicknesses. On the bottom left, you have a zoomed in image of the calcium. And right next to it, you have the background, which is taken right next to the calcium, so where it's all black. As you can see, the background doesn't really change across all the trials, which is expected. But then the calcium, it starts off as really, really pretty high resolution of like a lot of light. And then as you start moving up in slice thickness, the calcium starts getting more blurred. It becomes more blocky, and then at the end, it just becomes black, so it's indistinguishable from the background. So then if you look at the SNR plot right here, when it starts off at 0.7, you get a really, really high SNR. And it's interesting that at 2.5, you see a really sharp drop off. So that's kind of like a cutoff. Or before that, you have this SNR decreasing a little bit, but not nearly as drastically as once you hit 3 millimeter. But then this is only for the 6 millimeter calcium. So then we say for the 6 millimeter calcium, the industry standard of 2.5 is pretty good imaging for it. But if you wanted to image calcium sizes that are lower than 6 millimeter, maybe 2.5 might not be enough of a slice thickness. So to summarize our results, I'll hand it back to the top.
So in summary, we have shown that as slice thickness increases, the accuracy of detection of calcium decreases. Once again, to emphasize, the slice thickness is important because we want to avoid losing important information, which would help us provide the right diagnosis for a patient. Moreover, the industry standard of 2.5 millimeters was the least possible before slice thickness, before seeing a big drop in signal to noise ratio. Of course, we take this in concurrence with balancing X-ray dosage and acquiring a diagnostically useful image. And lastly, as Jason mentioned, we can see spatial Nyquist rates since calcium can only be reliably detected when the slice thickness is less than half of the calcium. Thank you for listening, and we'll be happy to answer any questions.
All right, thanks, guys. Any, yep, in the back.
Yeah, I just had a question. I'm a little confused about what you mean by slice thickness. So it seems like you're affecting slice thickness. Can you maybe enlighten?
Oh yeah. So technically, slice thickness is taken when you have your whole body image on the Z direction. So basically, how many divisions you split us down. So basically how many stacks you have of a whole person body. So then, but since we weren't able to acquire that data of the slice thickness from the CT because we have to run patients through the sample at different slice thicknesses, we decided to simulate that in a different direction. So we take one plane, we take one 2D image and we do the slice thickness across the y direction of that. So how many times we divvy up in like the other axes.
Oh, so it's like the y resolution in the y direction.
Yeah, so it's resolution in the y direction. Okay, I can't get the z direction data.
Okay. But that's if you did a CT. Okay.
Yeah. Yeah.
All right. Thanks.
And just so go to the table where you had the 7 millimeter and the number of views, right? So basically you're changing the in-plane resolution in the y direction by changing the number of projections. That's what you're doing here?
Yeah.
Okay.
So we just changed the number of projection on the
size.
I
thickness.
see.
So then the DL, we're basically changing DL when we take the rate function.
Got it. So it's that, yeah, so we're blurring in the L direction.
Yeah.
Is what we're doing as opposed to blurring in the Z direction. Okay, all right, interesting. I'm not sure, technically, like we tried to submit that as a paper, the reviewer would come back and say, wait a minute, that's not slice. That's, in plane. But it's very interesting results, right? That you showed how it drops away as this smoothing occurs in the L direction, or your loss of resolution in the L direction. That's interesting. And then the other thing is, when it got to signal to noise, you'd have to figure out, how the number of projections feeds into the final signal to noise of your data. Okay, I think we should keep rambling on. That was great. Thank you. All right, can you stop sharing your screen? Okay. And who's next? Oh, here we go. Thank you.
Good morning, everyone. So our group presentation will introduce you guys what is deep energy CT, which is also called spectrum CT. Can you go to the next slide, please?
It's not working.
Okay, it doesn't advance.
No, when I do it. Okay, there we go.
You got it.
Awesome. So before I can explain what is spectrum CT, I need to give you guys a little bit on the background information. So if you can look at the curve on the right, basically different materials have a different attenuation properties at different energy. Like the curve on the top show, which is the iodine, has a bigger attenuation property change when we change the energy compared to the curve at the bottom, which is a boron. So what spectrum CT really does is utilize these material properties and use two separated X-ray photon energies to create the image. And it allows us to separate materials like iodines from its surrounding tissue or its decomposition and permits the material classification. So there are mainly three types of spectrum CT available on the market. So the first one is the one on the very left, which is the dual source spectrum CT. So we have two sources that emit different energies. And because we have two sets of source and detectors, we can occur two sets of data simultaneously. By playing with each source, we can also optimizing the imaging qualities. The next type of design is the graph in the middle, which is a single source spectrum CT. So it has a source that can switch the energy they're gonna emit extremely fast. Because we only have one set of source and detectors, we can reach really good temporal resolution and have a full field of view. The last type of design we're gonna introduce is the one on the very right, which is the detector-based spectrum CT. So now the source emit a range of energies, and we have two layers of detector arrays for the detector. The top layer receives high energy and the bottom layer receives low energy. What it allows us to do is we will have color quantification and atomic information all in one scan. All three types of design is spectrum CT. They're just made from different companies and used for different purposes.
So the advantages and disadvantages of spectral CT are presented on this slide. Basically, an advantage is that their overall image quality does improve. The protocol robustness, which means that the DECT image allows for more troubleshooting without further imaging. Another advantage is the shortened patient length of stay. And a lot of times the images can be taken hours apart, and just to confirm if an issue needs immediate medical attention or if the patient is safe to go home. Next, potential radiation dose reduction, which is a very good thing. And for disadvantages, well, it requires a premium CT scanner that is 2 times
2 to 3 times the cost of a traditional scanner. It increased the image processing time, and there are additional prep required, additional training and maintenance.
I will now talk about the physics of spectral CT in relationship with the MATLAB simulation we found in literature. Utilizing X-ray measurements acquired at multiple energies, spectral CT has the ability to recover the concentration maps of the constituents of tissues in a quantitative manner. While the principle of dual energy CT has been known for more than 30 years, recent developments in energy selective photon counting detectors have boosted the research in this space. In this image here, we consider a polychromatic monoenergetic source and an object made of M materials, much like our human body, each with a unique density, which is imaged by a photon counting detector having I energy bins. At each projection angle theta, the photon counting detector provides I projection images known as SI theta. Repeating the acquisition for the desired amount of projection angles, we have the equation to the right, where G denotes the nonlinear forward model that takes into account the acquisition geometry and detector response function. While all of this is good, a challenge that exists with spectral CT is recovering material density from the energy resolved projection images S. One of the proposed solutions to this problem is material-dependent regularization for projection images using a Gauss-Newton algorithm. This simulation used a variational approach that corresponds with the Gauss-Newton algorithm to minimize the cost function of the projection images. Basically, the goal here is to minimize error and improve performance of the projected mass density of materials. Figure 2 depicts a colorized 3-material phantom showing soft tissue in yellow, bone in gray, and gadolinium in green. The resulting images are material decompositions to signify bone, soft tissue, and gadolinium using the Gauss-Newton regularization method with a global regularization parameter of 10 to the minus 0.5. The higher differential attenuation of bones as a function of energy compared to soft tissue allows the ability to decompose 2 images taken at different X-ray energies into tissue selective representation of the anatomy, as seen in the soft tissue only and bone only images. Although not mentioned in the study, it should be known that various literature suggests that dual energy CT provides higher signal to noise and contrast to noise values relative to traditional CT images. And although there's no comparison here, it's clear that this simulation uses the principles of dual energy CT to perform a robust material decomposition to isolate certain components of the human body.
So since it is quite complex to generate a script for spectral CT, we decided to provide a simple description for which can explain what happens. So we start off on the left side with a red cross, an image of a red cross, which represents a low energy image, let's say around 80 keV. Then in the middle, we have a higher energy image, which is a blue cross, let's say at 140 keV. From there, we combine those two to make a high energy spectral CT image output, which represents a purple cross. Essentially, one image with 2 different applied energy levels, which can represent how a spectral CT machine would provide its output.
So here are a few examples of the clinical applications for spectral CT. So the first is the bone removal tool. One example of this capability is it basically filters out the bone pixels because of the X-ray attenuation differences in the bone versus the iodine in the blood vessels. So it's easy to see the advantage of this tool because in the original image or figure A, the bones completely block out the view of the blood vessels, but in the 2 images, B and C, the blood vessels can be seen with great detail. So the next thing I want to talk about is the spectral CT has the capability to better differentiate between materials of different compositions. So for example, calcium-based stones versus uric-based stones. So in traditional CT, which is seen in figures A and B, both appear the same. So they're just bright white dots. But in spectral CT, which is the figures on the left, the calcium-based stones can be seen as blue dots and the uric-based stones can be seen as red dots. It's kind of hard to see, but if you look past the yellow wording, you can see the red and blue dots. So in this case, spectral CT improves the confidence of diagnosis and also the treatment effectiveness, because these two kinds of stones are treated much differently. This technology can also be modified for a wide range of applications as needed. So an iodine map from spectral CT shows the distribution of pulmonary perfusion in the lungs, which is basically showing the blood flow to every area of the lung. The dark spots indicate where blood is not flowing and therefore the lung is not working. These iodine maps are especially useful for evaluating lung function and identifying small pulmonary embolisms that would otherwise not be identified by traditional CT. So next is edema identification. So gout is a condition where urate crystals are present in the joint fluid, which causes the patient pain and swelling. This condition is traditionally difficult to diagnose. As you can see in the middle image showing traditional X-ray imaging, it's not very clear the cause of the pain and swelling. However, with spectral CT, we can easily confirm the diagnosis because it easily depicts the presence of those urate crystals, which are shown in green based on the difference in composition. Spectral CT also reduces the presence of artifacts. So if you have metal pieces, such as spinal screws, these cause beam hardening artifacts in image. So using spectral CT, these artifacts can be reduced to the point of almost no interference with the image. Also, post-image processing helps this out, so that can be applied to images to further improve the quality. So these are our references, and thank you. We will take any questions.
All right. Any questions from the students? So you made the statement that it could lead to dose reduction. Can you amplify on that to some extent? Because my feeling is that if you have to take 2 images, you have to split the dose somehow. But if you have to take 2 decent images at 80 kV and 140 or something, you would increase the dose.
So I guess the main idea behind that is that if you can troubleshoot with a problem with one image taken by, yes, the 2 scanners, but ultimately you're reducing it because you don't have to go back and take additional X-ray images. So that's why I kind of put it the potential, because if you have one image of traditional CT, one image of dual energy CT, it's not really very much different. But if the patient has to come back fewer times for images because these images are better, then it is a radiation dose reduction.
Okay, so it's kind of application specific, not kind of a physics problem where we could make a better picture with less dose. Okay.
Yes.
Got it. All right, great. Any questions from the audience? Okay, thanks very much. And I guess we're moving on to the last group, right? Yeah. Oh, 2 more? We got 2 more? Okay, 2 more. Sorry.
And we're gonna have 1 person present online.
Okay.
And then us 3.
Okay, and they're online now, so they
Yes.
can talk over and you can move the slides. Okay. All right, perfect.
I would unmute.
Yeah, you can just talk loudly for the room and it'll get picked up on your mic for the folks online, I think.
This is mine, and this is Joey, and we have Mabel online. So Mabel, if you comfortable, you can go ahead and start.
Hi, can you hear me well?
Yes, we now can.
Okay. Next slide, please. Okay, so I'll be starting off with an introduction on motion and CT image quality. Patient motion during a CT scan can cause misregistration artifacts. This is due to the fact that motion generates conflicts within the developed projection data, thus causing artifacts in the reconstructed images. This includes shading or streaking, blurring, gaps, and overlaps in data. As you can see in figure 1, there's an example of diagonal shading degrading the image. Motion artifacts are dangerous in a clinical sense because they can lead to suboptimal interpretation of lesion detection, diagnosis, and stability assessments of lesions, especially in the case of chest CTs. As you can see in figure 2, motion artifacts are covering the hemorrhage in the right frontal part of the brain. Next slide, please. This is especially relevant because of all the artifacts encountered during CT scans. A majority of them are motion artifacts at 1.73%. 62% of these artifacts were present in the brain due to patient head motion, while 26% presented due to involuntary abdominal movement, and 11% were related to chest motion. Next slide. In the clinical environment, motion artifacts can initially be reduced by the operator by means of immobilization of the patient by means of sedation, utilizing the shortest possible scanning times, asking the patient to hold their breath to reduce respiratory motion, and aligning the tube with the primary direction of motion. Built-in features of the scanner may also reduce motion artifacts, like utilizing overscan and underscan modes, software correction, and cardiac gates. However, what about the motion artifacts that get through despite these precautions? They can also be reduced via post-image processing. By simulating motion, algorithms and trained neural networks can potentially be used to reduce artifacts in the clinical setting, as well as prevent the need to rescan. Next slide.
Okay, now I'm going to talk about what kind of simulation we did. So first, the motion type, we split the motion into discrete motion and also continuous motion. So for this discrete motion, it's like rotating the scanner, and at a certain angle, it just moves here to here. So this is the only thing you can do in the simulation, because in real world, we only have the continuous motion on the body, right? So we're also going to show it in different direction, like in just single direction and also in both direction, and also to show the whole picture of this motion effect. We're going to show the impulse function so that you can get the very small pixel. What does it change when it encounters motion? And also we're going to show a much more complex signal, phantom. Also, we're going to use different reconstruction methods to show so the parallel beam and fan beam, what's the difference between them. Okay. So this is a little GUI, and if we generate a point spread function, everything seems normal, right? So if we shifting X, and this is this CT scanner, it rotates at 360 degrees, and we start at 90 degrees. So it will appear as a sharp here. And you can see it actually moves here from here because it's this signal, it provides 1/4 of it, and this signal it provides 3/4 of it. We can also see some artifact. It looks like a curve or something. Yeah. And if we change it to 180, actually it got the signal that's basically equals to each other. After it changes, yeah, it just appears to be here. So when we do funding, this is with no motion. You can see it actually costs more artifacts, but if you watch closely enough, these two lines, they are intersect in a point, and you can see it better with the phantom. So for phantom, if you look at the parallel, this artifact line, it actually parallels to each other, right? But if we use the funding, the artifact would actually look like a funding line, right? Yeah, so this is what we did in discrete motion, and next, so we will talk more about it.
Yes, so before we talk about continuous motion, there's actually a little bit of an edge case we should cover. So as you can see on the left, there are two squares. The larger square is moving while the smaller square is not moving. So in clinical cases such as the chest and CT scan, it's very likely that the spine of the patient is not going to move, but the heart is beating all the time. So to simulate that, we generated this two figure and then generated scenario of the parallel beam and the same beam. As you can see, for both scenarios, there is one line, there is a line with the last width representing the smaller block, and the line with larger width are representing a larger block. As you can see in the middle, there is some very sharp discontinuity. And then the reconstructed image is the third one from the left. As you can see, for the parallel beam one, the artifact is more vertical, is more horizontally aligned, but for the scenario with the same beam, actually a little bit, I'll say like goes all the way. However, if you take a look at the smaller square, it doesn't seem to have artifacts on them. And you might wonder, what if, since like for the case we just demonstrated, have the two squares separate quite far away, what if we have it closer? Turns out, even if we place a smaller block closer, as long as it doesn't move, it doesn't seem to have any artifact on it. So here we are going to simulate a pseudo continuous motion. So by pseudo, I mean we're simply doing a very small step discrete motion multiple times. As you can see on the left, that's the same square we're trying to move, and in the middle is a sinogram of the square of the moving. So the method we try to like simulate this continuous motion is we'll move every 1 pixel every time the projector rotates 1 degree. So effectively we can move to the right by 10 pixels in 10 degrees, and actually within the red square is where the discontinuity occurs, but because we're in such fine step, that's not really very obvious. However, when we reconstructed it, you can see similar like behavior existed for the parallel beam. The artifacts are more horizontally or more vertically aligned, but for the ending point actually goes further.
So one of the other things we wanted to consider was the discrete sampling that is caused by a CT scanner. The motion caused by the patient will not only be continuous in time, but also continuous in space. However, when we're sampling that, we end up with those discrete samples. So how this looks when considering very small motion, changes similar to the size of an actual detector. It appears much more like a percentage shift of intensities rather than some sort of object moving over. So what we did here was model this both considering the discrete sampling of space and the continuous sampling of space, as shown in the last video. And the sinogram, as you can see here, changes depending on whether or not we are using the discrete sampling or the pseudo continuous sampling, as we call it, because of course it's still discrete, just much less so. And then the other fact that we're changing here, and why it's a video, is we are modeling the amount of shifts. So like in the previous continuous video or continuous slide, as the video changes, the number of samples over time is changing. So you can sort of see the different splits in the sinogram. And what this allows us to do is see the change as it becomes more continuous. So you can see what it might look like when it is actually continuous. So, sorry. What this video shows is a resulting point spread function where we have the initial result with no motion. And then we have the point spread function of the pixel moving over one pixel, increasing the amount of times we're changing that movement. And what we can see here actually is that there's very little difference between this discrete sampling or our pseudo-continuous sampling. But why this is relevant is because if you're considering motion less than the amount or the distance of your detector, what ends up happening is the less, the smaller the movement, the larger a difference there is in the discrete shift versus the pseudo-continuous shift. So what I'm showing here is the point spread function, where as the video plays, it will show pixel movement where it is moving over less and less. So here, the pixel is moving over one full pixel. Pre-loss in connection.
Oh, you guys are, oh, okay. Okay. Oh, darn. You want to try doing it again? Are you like, you're gone still?
Yeah.
Okay.
Yeah, so as this video plays, the pixel will be moving over less and less distance. So what you can see here is that if the motion is less than a single pixel, what ends up happening is with our discrete model, you can see that there's more of this shadow effect and less of the streaking effect that we see. This means for small motion or small shifts, we should consider this shadowing effect more than the streaking effect.
All right. We're gonna have to wrap it up because we're running over time. Okay. Great, thanks. Any questions on the simulation? Okay, so in order to make it on time, we're gonna like switch to the next team. Okay. Okay.
Hi
Take it away.
everyone, we're group 12 and we will be presenting on band beam reconstruction. So first we'll do a brief review of CT. As we know, it uses projection data to reconstruct cross-sectional images, also known as tomograms. And the goal of CT is to reconstruct the value of the X-ray attenuation at each pixel. An important concept we learned about is the 2D radon transform. And to understand it, we can first look at a single 1D projection given by GL theta at a fixed theta, as seen on the bottom right image. And for each G, we can see that it equals to the sum of the X-ray attenuation along that line, also indicated by the equation on the left. And after getting many 1D projections over multiple angles, we can compile the projections into a sinogram, which visualizes the 2D radon transform of our original image. So this is just a visual summary of the parallel beam, which we learned in class, and a fan beam, which we will go into more detail on the following slides. As seen on the top right image, for the parallel beam, the X-rays come from multiple sources and travel parallel to each other. Whereas in the fan beam, as seen on the bottom right, the X-rays emanate from a single source and spread out like a fan.
So in order to develop the fan beam reconstruction, we will need to understand the parallel beam reconstruction. So the image on the left shows a visual representation of the lines of projection of the parallel beam. And L represents the lateral position of the lines, and theta is an angle unit or angle of a unit normal to the line. And each line can be represented as the equation x cosine theta plus y sine theta equal to L. So to find the 2D radon transform, as Rosie was saying, we integrate the image, which we'll call, or the object, which we'll call f of x comma y, across the x and y plane, only where it is along the line, which is represented by this 1D impulse function, because it causes the integrand to be 0 everywhere except on the line. Next, we take the 1D Fourier transform of the radon function of the 1D Fourier transform of the radon transform to get G of rho comma theta, where rho is the spatial frequency. G of rho comma theta is equal to the 2D Fourier transform of the object f of x comma y. So this is known as the projected slice theorem, which basically states that the 1D Fourier transform of a projection is equal to the is a slice of the 2D Fourier transform of the object. So we're going to skip over some things, but the most important part is that from the convolution theorem of the Fourier transform and using the filter back projection and the projection slice theorem, we may rewrite the equation of the convolution of C of L and G of L comma theta, where C of L is the inverse radon transform of the spatial frequency of the 1D Fourier or the inverse 1D Fourier transform of the frequency filter. And so this is known as the convolution back projection and will be used to construct the fan beam reconstruction. So to start to develop the fan beam reconstruction, we're going to look at the visual representation of the lines, just like we did in the parallel beam. So in this case, we could represent the lines in terms of beta and gamma, where beta is the angle between the source and the y-axis, and gamma is the angle between the source and the middle of the projector. And we could see that beta is related to beta and gamma by adding them up, and L is equal to D times sine of gamma, where D is the distance between the source and the origin.
All right, for our next steps, we'll need to convert the coordinate system from Cartesian to polar. For this, we're going to define new values for x and y. So x is going to be just r cosine phi, y is going to be r sine phi. We're going to plug this back into the equation that Igor spoke about, and using trig identities, we can simplify that a little further there as highlighted in red. So for our next steps, we're going to change. We'll have to change the variables of integration, and to do that, we'll because this transformation is nonlinear, we'll also need to multiply this equation by the Jacobian. So as Igor mentioned earlier, for the value equations for theta and L, we'll have to take their partial derivatives with regards to with respect to beta and gamma. So as you can see here, once you take the determinant of that, we'll get d cosine gamma, and we'll have to multiply that to the equation we found earlier. So substituting the values for theta and L back in the equation and adding the Jacobian here in red, we get this equation here. We're going to, in the last step, we're going to change the limits of integration. So beta goes from 0 to 2 pi. We read that 0 to 2 pi because it's periodical. And the limits gives us just the angle between the center line and one edge of the fan. So what you can see highlighted in yellow here is the fan beam analog of again the radon transform there. So there's a lot of math and derivation that we won't necessarily deep dive into, but for our next step is we're kind of picking an arbitrary point here and defining a couple new variables, d prime, distance between that arbitrary point in the source, and gamma prime, which is the angle between the center line and that rate that's not passing through the point. Again, what I would kind of focus on is kind of the highlighted sections, because that's going to show you what simplifications we're moving from each step to the next. So as you can see, the reason why we're doing this becomes clear because it now starts to resemble a convolution back projection. So you will see how it's the basic convolution where your the projection is involved with that filtering function, the weighted filtering function there. And this can be further simplified and written down into this equation as shown in the red box below.
All right, so we're just going to walk you through the equations, the visual representation. So we're just going to walk you through what the parallel beam projection as well as the fan beam projection. And we've used the shuffled and head phantom to carry out the simulation. So the first step that we did and we wanted to show is the sinogram of the phantom using the parallel beam projections. And we've done this using different number of projection angles. So we kept the range of theta constant, which is from 0 to 180. And in order to show you how the sinogram quality gets better, we've basically gotten the images at 9, 18, and 180 projection angles respectively. There's no particular reason for selecting these number of angles, it's just to show the difference in the quality of image that you obtain. And this is sort of translated when you do the parallel beam reconstruction and get back the image as well. Here we've done that using the Ramlak filter. And as you can see, when the number of projection angles is less, the quality of the image is significantly lower. This is consistent with what we learned in class and what we did as part of our assignment. So the next part would be to do the fan beam reconstruction itself. So unlike parallel beam reconstruction, where the image is dependent on the number of projection angles you have, fan beam reconstruction is dependent on the angle of spacing between the projections. So lower the spacing, that is lower the angle between two projections, better the quality of the image. Intuitively, if you think about it, that would happen if you have a lot of projections. So if you had a lot of projections that are closely packed together, the angle spacing would be lesser and the quality of image would get better. But that just means you'll be making compromise between having more projections and more dosage and to get a better quality image. So another thing that we wanted to talk about is the para to fan and fan to para functions that MATLAB offers that could basically translate parallel beam data to fan beam data and fan beam data back to parallel beam data. So MATLAB does this by making use of a function called fan sensor spacing, which basically varies the angle spacing between the projections. And it also makes use of another function called parallel fan spacing, which would vary the number of projection angles that you use in the parallel beam projection. So if you were to use the function para to fan on a parallel beam data, it would store the data in a column of it would store the data in a matrix where the columns would represent the rotation angles and the rows would represent the sensor locations. And by using the function fan to para, you can successively recover your original parallel beam. So to just leave you all with a thought, fan beam projection can be computationally expensive. So if you wanted to just have a rough idea and do like a quick way to get to fan beam projection from parallel beam projection, you could just sort the fan beam projection into a bunch of parallel beam projections. This would be a very bad approximation mathematically, but computationally it would be easier. So This could happen if you had a lot of projections at a lot of angles, such that you could just say that the projection at the n plus 1 standing vertex is equal to the projection at n standing vertex. That would be wrong mathematically. I mean, not wrong, but it would be a bad approximation, but it would give you, it would allow you to calculate the time being image of decent quality. So
Thank you.
that was the end of our presentation, and you're open to any questions.
Great, thanks. Any questions? So when you say that approximation is mathematically, you said it was poor.
Yeah.
However, I mean, if you take enough angles, right?
Yeah, exactly. So that would just mean you're using a ton of dosage, and
Right.
you're sampling it at almost every point possible. So you have so many projection angles that the difference, that the spacing would be almost constant at each of
The
the
same,
points. Yeah,
right.
so
Yeah. So I think it just depends on if you can interpolate between those two cases,
Exactly.
between the parallel and between the fan.
yeah.
You know, without a great loss of information, then you're, you know,
Yeah,
it's
then you're
about
good.
the
Yeah, you're
same.
basically okay.
Okay, terrific. All right, thanks. And thanks everyone for putting a lot of work into those presentations. That was, as usual, a lot of fun. Okay, so we'll see you on Monday and we'll continue with MRI.